In this vast, boundless universe, Earth cannot be the only planet to have nurtured life. So the question arises, if extraterrestrials truly exist, where on Earth are they? This simple inquiry posed by Nobel laureate physicist Enrico Fermi, over half a century ago, conceals one of contemporary astronomy's most famous and thought-provoking paradoxes, Fermi's paradox. At the core of this paradox lies a sharp contradiction. On one side, based on cosmic scale and physical laws, theoretical calculations suggest a cosmic clamor. The universe should resound with the murmurs of life and the clamor of civilizations. Yet, on the other side, our actual observations reveal perplexing silence. Our most sensitive radio telescopes, pointed toward the heavens, capture only the natural pulsations of stars and the physical noise of interstellar medium. It seems as though humanity is the sole being in the vast cosmos, capable of thought and inquiry. Tonight, let us embark together on this journey of the mind, temporarily setting aside the concerns of daily life, and cast our imaginations toward the deepest reaches of the cosmos. We shall delve into this fascinating realm where scientific conjecture and philosophical speculation intertwine, to systematically explore the myriad possibilities explaining why the universe remains so silent. We begin with the grand scale of the cosmos, understanding the Drake equation's optimistic estimates of civilization's abundance. Then confront the practical challenges of the search for extraterrestrial intelligence, and delve into the somewhat unsettling theory of the Great Filter. It may explain why the cosmos remains so silent. We'll also examine other intriguing hypotheses, from the idea that we are cosmic premature babies, to the possibility we inhabit a universe-wide zoo. This exploration offers no definitive answers, but the journey itself will profoundly transform how we view ourselves and our place in the cosmos. Now, prepare your curiosity. Let us embark on this mental journey through time and space, to confront the ultimate puzzle the universe has left us. Beginning with our most familiar solar system, this marks the starting point of our cosmic exploration, and the most thoroughly understood home within human comprehension. The solar system centers around a G-type main sequence star called the Sun. This star accounts for 99.86% of the solar system's total mass. Its powerful gravity binds together 8 planets, several dwarf planets, over 200 moons, and countless asteroids, comets, and interstellar dust particles into a complex, dynamically balanced celestial system. Mercury is the closest planet to the Sun. Its surface is pockmarked with craters. Day-night temperature variations are extreme. Venus is shrouded in thick sulfuric acid clouds. The greenhouse effect makes its surface hot enough to melt lead. Earth lies within the perfect habitable zone, possessing liquid water, moderate temperatures, and a stable atmosphere. Mars, the red planet, features massive volcanic canyons and ancient riverbed traces, suggesting water may have once flowed there. Beyond Mars' orbit lies the outer region of the solar system. Jupiter, the largest gas giant in the solar system, possesses a mass 2.5 times greater than all other planets combined. Its famous Great Red Spot is actually a massive storm system that has persisted for centuries. Saturn is renowned for its magnificent ring system, composed primarily of ice crystals and rocky debris, which exhibit breathtaking beauty when illuminated by sunlight. Uranus and Neptune are ice giants, composed largely of water, ammonia, methane, and other icy substances, orbiting in the cold outer reaches of the solar system, with Neptune's orbit marking the boundary of the solar system's main body. Its diameter spans approximately 9 billion kilometers. Yet the solar system's true influence extends far beyond this. The Kuiper Belt, a disk of icy bodies beyond Neptune's orbit, contains numerous dwarf planets like Pluto. Further still lies the Oort cloud, a hypothetical spherical cloud of icy objects, whose outermost edge may extend over a light-year. This represents the theoretical boundary of the Sun's gravitational influence. The farthest human-made probe to date, Voyager 1, launched in 1977, has traveled at approximately 17 kilometers per second for over 4 decades. It has just crossed the heliopause, the boundary where solar wind meets interstellar medium. Yet even at this speed, exiting the Oort cloud's boundary would require tens of thousands of years, a timescale far exceeding the entire recorded history of human civilization. Now let us elevate our perspective to the scale of the Milky Way. When we gaze upon that milky band across the night sky, we are observing the disk structure of the Milky Way. Our solar system is embedded within this vast stellar collection. The Milky Way is a classic barred spiral galaxy, with a diameter of approximately 100,000 to 180,000 light-years, a central bulge thickness of about 10,000 light-years, and an average disk thickness of roughly 2,000 light-years. It contains between 100 billion and 400 billion stars, along with vast quantities of star clusters, nebulae, interstellar gas, dust, and dark matter. All this matter rotates together around the galactic center. The Milky Way's structure can be broadly divided into several main components. The galactic bulge is the centrally raised, spherical region of the Milky Way. Here, stellar density is extremely high and hosts a supermassive black hole with a mass equivalent to 4 million suns. Sagittarius A*. The galactic disk forms the main body of the Milky Way, a flat, disc-shaped structure composed of stars, gas, and dust. Within it lie several major spiral arms, such as the Perseus arm, the Sagittarius arm, and the Ruler arm. Our solar system resides within a minor spiral arm called the Orion arm, approximately 26,000 light-years from the galactic center. The galactic halo is the nearly spherical region enveloping the disk, containing ancient stars and globular clusters, along with vast quantities of dark matter. If we were to scale down the Milky Way to the size of a standard football field, the actual size of our solar system would be smaller than a speck of dust on the field, barely discernible even under an electron microscope. This scale of comparison profoundly reveals how utterly insignificant our home is within the Milky Way's grand architecture. Traveling across the galaxy at light speed would take 100,000 years, a figure beyond human intuitive grasp. Consider a more concrete comparison. A modern commercial airliner flies at approximately 900 kilometers per hour. Traveling at this speed from one end of the Milky Way to the other would take over 12 billion years. This duration is even longer than the current age of the universe, which is 13.8 billion years. The Milky Way itself is not isolated. It is a member of the local group. The local group spans a region of space approximately 10 million light-years in diameter and contains at least 80 galaxies. The Milky Way and Andromeda are the two dominant galaxies within it. Andromeda is the largest galaxy in the local group. It is approaching the Milky Way at a speed of about 110 kilometers per second. It is projected to collide with the Milky Way in approximately 4 billion years. Ultimately, they will merge into a massive elliptical galaxy. The local group is further embedded within the larger Virgo supercluster. This supercluster spans a diameter of 110 million light-years and contains over 100 galaxy groups and clusters, totaling approximately 30,000 large galaxies. Our local group resides in the outer regions of the Virgo supercluster and is being pulled by its gravitational field. Recent astronomical research has uncovered an even more colossal cosmic structure, the Laniakea supercluster. This name originates from Hawaiian, meaning endless heaven. Its extent spans over 520 million light-years, encompassing roughly 100,000 large galaxies, with a total mass equivalent to 100 billion times that of the Sun. Within the Laniakea supercluster, all galaxies slowly drift toward a gravitational center known as the Great Attractor. Now let us turn our gaze to the ultimate frontier, the observable universe. This is the entire region of space, where light has had sufficient time to reach us since the Big Bang 13.8 billion years ago. Its diameter reaches 93 billion light-years. This figure far exceeds the simple product of the universe's age and the speed of light, because the fabric of space itself is expanding at an accelerating rate. The observable universe contains a staggering number of celestial bodies, based on deep-field observations from the Hubble Space Telescope, and comprehensive estimates from other astronomical data. Astronomers believe at least 2 trillion galaxies exist within the observable universe. This figure is more than 10 times higher than estimates from the late 20th century. Each galaxy contains an average of 1 to 10 trillion stars. This implies the total number of stars in the observable universe is approximately 100 trillion. Let us attempt to grasp the significance of this figure. The total number of grains of sand on all Earth's beaches and deserts is estimated at approximately 7.5 times 10 superscript 1. Yet this number represents only a minuscule fraction of the universe's stellar population. In fact, the number of stars in the cosmos exceeds the quantity of Earth's sand by several orders of magnitude. On such a vast cosmic scale, our home planet truly is, as Carl Sagan described it, a mere speck of dust suspended in a sunbeam. Upon this speck, every person you love, every person you know, every person you've ever heard of, and every person who has ever lived, spends their life. Understanding the vastness of the space-time structure we inhabit is the first step toward resolving the Fermi Paradox. It establishes a fundamental premise: a universe containing trillions of galaxies, each galaxy containing hundreds of billions of stars, each star potentially hosting multiple planets. Under the universal application of physical laws, the foundation of matter and energy is so profound that even if the probability of life emerging is minuscule, given such an immense base number, the absolute quantity that ultimately arises should still be remarkably substantial. When discussing potential life in the universe, we must first grasp the sheer scale of possibility the cosmos itself offers. From the minute solar system to the vast observable universe, each leap in scale reveals new possibilities and provides the fundamental backdrop for understanding the Fermi Paradox. This forms the bedrock of theoretical discourse. We shall now continue exploring the possibility of life. Against this vast space-time backdrop, life has blossomed in such diverse forms on Earth. This compels us to ponder a fundamental question. Is Earth's life the sole miracle in the cosmos? Or is life actually a universal outcome of cosmic material evolution? To answer this question, we must first investigate whether the fundamental building blocks of life are universally present throughout the universe. Modern biochemistry informs us that life on Earth is primarily carbon-based and relies on other crucial elements like hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements are not unique to Earth. They all originated in the fiery stellar furnaces deep within the cosmos. During the primordial nucleosynthesis phase at the dawn of the universe, only the lightest elements, hydrogen and helium, were produced, along with trace amounts of lithium. All the heavier elements necessary for life must be generated through nuclear fusion reactions within stars. This process is known as nucleosynthesis. smaller stars like our Sun fuse hydrogen into helium through the proton-proton chain reaction in their cores. Toward the end of their lives, they generate carbon and oxygen via the helium flash process and scatter these elements into interstellar space. The evolution of massive stars is more dramatic. They burn in layers like an onion, successively fusing hydrogen, helium, carbon, neon, oxygen, and silicon in their cores, until reaching the most stable element, iron. When nuclear fusion can no longer generate sufficient energy to counteract gravity, the star undergoes a supernova explosion. This most spectacular cosmic explosion releases more energy in an instant than the star produced throughout its entire lifetime. Under extreme temperatures and pressures,
Rapid neutron capture processes.
create heavier elements like gold and uranium. Additionally, extreme astrophysical processes like binary neutron star mergers are also considered significant sources of heavy elements. These elements forged by stars mix with interstellar gas and dust to become the raw material for forming new generations of stars and planetary systems. Our solar system itself is composed of remnant matter from previous stellar generations. Thus, every carbon atom, every oxygen atom, every nitrogen atom that constitutes life on Earth was once forged within one or more long-extinct stars. Astronomical observations have confirmed the cosmic ubiquity of these building blocks of life. Through spectroscopic analysis, we have detected a rich variety of organic molecules within interstellar molecular clouds. These vast cosmic clouds serve as the cradles for the birth of stars and planetary systems. In famous star-forming regions like the Orion Nebula, scientists have discovered simple molecules such as water, carbon monoxide, ammonia, and methanol. In more complex dark molecular clouds like the Taurus molecular cloud, an even richer variety of molecules has been detected, including cyanoacetylene, formamide, and even precursor molecules to the amino acid glycine. Particularly exciting is the discovery of multiple amino acids and nucleic acid bases, fundamental building blocks of life, in samples of primordial solar system material like comets and meteorites. This strongly suggests the chemical foundations of life may have been widely present in primitive planetary matter during the solar system's early formation. Beyond chemical elements and organic molecules, a suitable environment is also essential for life's emergence. In planetary science, the concept of the habitable zone is paramount. It refers to a theoretical region around a star, where surface temperatures on planets can sustain liquid water. For G-type main sequence stars like the Sun, the habitable zone spans approximately 0.95 to 1.37 astronomical units. Earth happens to lie near the center of this zone. For smaller, dimmer M-type red dwarf stars, their habitable zones are much closer, possibly only 0.1 to 0.2 astronomical units. However, planets here face the issue of tidal locking, where one side perpetually faces the star, while the other remains perpetually dark. It is noteworthy that the concept of the habitable zone is continually expanding and deepening. It is no longer confined solely to the surface conditions of planets orbiting stars. Jupiter's moon Europa and Saturn's moon Enceladus both possess thick icy crusts, yet beneath their ice, tidal heating may sustain liquid oceans or even hydrothermal vents. These locations are considered prime targets for seeking extraterrestrial life within our solar system. This has introduced the concept of the subsurface habitable zone. On a galactic scale, scientists have also proposed the concept of the Milky Way's habitable zone. This region lies at a distance from the galactic center that is neither too close nor too far Too close would expose it to frequent lethal radiation from supernova explosions and gamma-ray bursts. Too far might lack sufficient heavy elements necessary for forming rocky planets. From a chemical perspective, the unique electronic structure of carbon atoms enables them to form 4 strong covalent bonds and connect with other carbon atoms to form chains, rings, and complex networks. This bonding capability forms the foundation for building biological macromolecules like proteins and nucleic acids. While theoretically other elements like silicon could serve as life's building blocks, silane compounds are far less stable than carbon chains and readily decompose in liquid water environments. This makes carbon the most likely ideal scaffold for complex life chemistry in the universe. Water molecules, owing to their polarity and potent hydrogen bonding capacity, serve as an irreplaceable biological solvent. They dissolve diverse ions and polar molecules, facilitate intricate chemical reactions, and transport nutrients and metabolic waste across cellular membranes. The search for extraterrestrial life largely equates to seeking evidence of liquid water. Reflecting on Earth's evolutionary journey, we uncover clues suggesting life's potential ubiquity. Shortly after Earth's formation, when its surface remained a molten magma state, the earliest life forms may have already begun to emerge. The earliest microbial fossil evidence discovered to date dates back to 3.5 billion years ago, or even earlier, while Earth itself formed 4.5 billion years ago. This implies that life rapidly emerged, once Earth's environment stabilized sufficiently to support it. This swift emergence suggests that, under suitable conditions, the birth of life may not be an extremely rare event, but rather a naturally occurring process. The Miller-Urey experiment first demonstrated in the 1950s that, under simulated conditions of Earth's early atmosphere and oceans, with energy inputs like electrical discharges, various amino acids and other building blocks of life could be produced from inorganic substances. Subsequent, more complex experiments even synthesized nucleotides and lipids. Together, these experiments indicate that the pathway from chemical evolution to biological evolution could occur on many Earth-like planets throughout the cosmos. In summary, the fundamental chemical elements constituting life are widely distributed in the universe. Complex organic molecules are commonly found in interstellar space and planetary systems. Environments suitable for liquid water may exist in astonishing numbers across the Milky Way. The fact that life emerged rapidly on Earth further strengthens our confidence in the universality of life throughout the cosmos. All this evidence points to one conclusion: life is likely not unique to Earth, but a natural product of cosmic material evolution. This provides another crucial theoretical pillar for the Fermi Paradox. As we gaze into the vast depths of the Milky Way, a question naturally arises. Among these hundreds of billions of stars, how many intelligent civilizations exist that could communicate with us? To provide a scientific framework for this seemingly fantastical question, astronomer Frank Drake proposed a famous equation in 1961. This equation is now known as the Drake equation. It attempts to break down the grand quest for extraterrestrial life into a series of probabilistic factors that can be systematically explored. While it cannot provide a definitive answer, it offers a systematic way of thinking to assess the probability that we may not be alone in the Milky Way. The basic form of the Drake equation contains 7 key variables. The product of these variables ultimately yields the number n of advanced civilizations within the Milky Way that might potentially contact us. Let us delve into each of these variables and modern science's understanding of them. The first variable is the average rate of star formation in the Milky Way. This figure describes the number of new stars born annually within our galaxy. Based on astronomical observational data, astronomers estimate this figure to be approximately 1 to 3 stars per year. We can take an intermediate value, such as 2 stars per year, as a starting point for our calculations. The second variable is the fraction of these stars that possess planetary systems, FP. At the time Drake proposed the equation, this remained a pure conjecture. But today, the rapid advancement of exoplanet science has provided a clear answer. Data from observatories like the Kepler Space Telescope indicate that the vast majority of stars possess planetary systems. This proportion may reach as high as 80% or even approach 100%. This implies that planetary systems are a natural byproduct of star formation, rather than a rare phenomenon in the cosmos. The third variable is the number of planets within the habitable zone of each planetary system, denoted as NE. The habitable zone refers to the region at just the right distance from the star, where liquid water can stably exist on the planet's surface. Statistical analysis of known exoplanetary systems suggests that on average, each star system may host between 0.2 and 0.5 rocky planets within a conservative habitable zone. This implies that within the Milky Way, billions to tens of billions of planets possess the potential conditions for fostering life. The fourth variable is the proportion, FL, of these habitable planets that actually develop life. This is one of the greatest unknowns in the equation. Our sole sample is Earth. Life emerged relatively soon after Earth's formation, suggesting that given suitable conditions, life's emergence may be a natural and rapid process. Yet we remain uncertain whether this is a universal pattern. Scientists' estimates span a vast range, from the extremely pessimistic near zero to the quite optimistic near 100%. The fifth variable is the proportion of these life forms that evolve into intelligent civilizations, phi. Even if life is ubiquitous, does it inevitably evolve into technological civilizations like ours? Earth's history of life tells us that the journey from simple life to complex multicellular organisms took over 3 billion years, while the emergence of technological civilizations occurred only within the last few tens of thousands of years. This evolutionary path may be fraught with serendipity, making phi an extremely uncertain parameter. The sixth variable is the proportion of these intelligent civilizations that develop interstellar communication technology and possess the willingness to engage in communication, denoted as FC. A civilization might refuse contact due to philosophical or religious beliefs, or simply lack interest. Alternatively, differing technological paths could lead them to employ communication methods we cannot yet comprehend or detect. For instance, they might utilize neutrino communication, or manipulate space-time structures to transmit gravitational wave signals. Such technologies far exceed our current detection capabilities. The seventh variable, and the most speculative one, is the average lifespan L of these technological civilizations. How long can a civilization, from mastering interstellar communication to its eventual demise, sustain the transmission of detectable signals? This directly impacts our probability of discovering them. Human civilization has only entered the technological era within the last century. We possess nuclear weapons and face global challenges like climate change. How long our technological civilization will endure, 1,000 years, 10,000 years, or longer, remains an open question. If civilizations typically collapse rapidly due to resource depletion, technological runaway, or self-destruction, then L could be very small. The number of civilizations coexisting in the Milky Way would also be extremely scarce. Multiplying these variables together yields the value of N, the number of advanced civilizations in the Milky Way potentially capable of contacting us. If we adopt more optimistic estimates, such as a star formation rate R of 2 stars per year, a planetary possession rate FP of 100%, an average of 0.5 habitable planets per system NE, a life emergence rate FL of 50%, an intelligent evolution rate Phi of 10%, a communication capability rate FC of 10%, and a civilization lifespan L of 10,000 years. The result is N equals 500. This implies that 500 advanced civilizations may exist in the Milky Way, meaning one civilized world for every 20 million stars. However, if we use more pessimistic parameters, especially when the civilization lifespan L is considered very short, such as only a few hundred years, then the value of N could rapidly drop to 1, or even less than 1. This suggests that human civilization might be the only technological civilization currently existing in the Milky Way. The value of the Drake equation lies not in its ability to yield precise numbers. In fact, due to the extreme uncertainty surrounding multiple parameters, any specific calculation can only be regarded as conjecture. Its true significance lies in transforming an abstract philosophical question into a scientifically explorable framework. It clearly identifies gaps in our knowledge and guides future research directions. Every discovery of an exoplanet, every breakthrough in the study of life's origins, helps us better constrain these parameters. This equation also profoundly reveals that the duration of a civilization's existence, L, may be the most crucial variable in the entire equation. It is not merely an astronomical figure, but concerns the very future of humanity itself. Whether we can solve the global challenges we face and avoid self-destruction, thereby extending the lifespan of our civilization, may ultimately determine if we can join that potential galactic civilization club. The Drake equation serves as a bridge, connecting our objective observations of the cosmos with profound reflections on the nature of life and civilization. It tells us that even by the most conservative estimates, among the galaxy's hundreds of billions of stars, we have ample reason to continue searching, to listen for faint echoes that might come from those distant skies. Let us turn back the clock of history to the mid-20th century. It was an ordinary summer day in 1950. At the lunch table of Los Alamos National Laboratory in the United States, a group of top scientists engaged in what seemed like casual conversation. Among them was Enrico Fermi, the Nobel laureate renowned for his research on neutron nuclear reactions. The conversation began with wild speculations about UFO news. The conversation drifted from wild UFO news to the possibility of extraterrestrial intelligent life. The atmosphere was relaxed and imaginative. After listening to his colleagues' speculations about interstellar travel, Fermi suddenly posed a seemingly simple, yet profound question that would resonate for over half a century. So where are they? This off-the-cuff remark later became known as the Fermi Paradox. Though initially just a casual query, it precisely captured a profound scientific contradiction that continues to perplex countless astronomers and philosophers to this day. To grasp the true power of the Fermi Paradox, we must return to the mental landscape in which Fermi posed this question. Fermi was a scientist renowned for his physical intuition and rapid mental calculation abilities. He excelled at breaking down complex problems into orders of magnitude estimates, a mode of thinking later dubbed the Fermi estimation. In his mind, a swift probability calculation was unfolding. The Milky Way hosts hundreds of billions of stars, and the universe is over 10 billion years old. This implies ample time for intelligent civilizations to emerge throughout the galaxy and develop interstellar travel technology. Even at extremely slow speeds, say 1/10 the speed of light, a civilization would require only a few million years. to colonize the entire Milky Way. Compared to the galaxy's age of billions of years, this timescale is but a fleeting moment. Following this logic, the Milky Way should already be teeming with traces of advanced civilizations. Our solar system may have been visited countless times. Earth's night sky should be dotted with the lights of alien spacecraft. Or at the very least, our radio telescopes should be capturing signals from civilizations deep within the cosmos. Yet reality stands in stark contrast to this theoretical expectation. The starry sky we gaze upon is utterly silent. Our signal-searching headsets only pick up the hiss of cosmic background noise. We find no conclusive evidence to prove the existence of other intelligent life beyond Earth. This vast gap between theoretical expectation and observational reality is the core of the Fermi Paradox. It is not a true logical paradox, but a powerful cognitive conflict. Compels us to ask, if the universe truly should be teeming with life, why do we see nothing? Why do we hear nothing? The Fermi Paradox can be succinctly expressed as the simultaneous validity of two propositions, creating immense tension. Proposition 1. Given the scale and age of the universe, and the universality of physical laws, intelligent civilizations should be commonplace throughout the cosmos. Proposition 2. We possess no reliable observational evidence to support such widespread existence. These two propositions are not directly contradictory logically, yet their simultaneous validity feels profoundly incongruous, as if some fundamental understanding of the universe is gravely flawed. Fermi himself may not have developed this question into a systematic theory, but his intuition pierced a crucial veil. Over the decades since, countless scientists have attempted to resolve this paradox. Solutions generally fall into two categories. Either acknowledge that intelligent civilizations are exceedingly rare, so rare that we may be alone in the Milky Way, or concede that some as yet unknown mechanism prevents civilizations from encountering or detecting one another. Let us dissect the reasoning chain underlying this paradox. First, the scale argument. The Milky Way spans approximately 100,000 light-years in diameter and contains between 100 and 400 billion stars. Many of these stars possess planetary systems, some of which lie within habitable zones, providing vast testing grounds for life. Second is the time argument. The Milky Way is over 13 billion years old. The solar system and Earth are relatively young, approximately 4.6 billion years old. This implies that before the solar system formed, the Milky Way had nearly 8 billion years to nurture earlier intelligent civilizations. Third is the argument from the principle of mediocrity. This principle posits that Earth, the solar system, and human civilization occupy no special position in the cosmos. If life and intelligence could emerge and evolve on Earth, then under countless similar conditions throughout the universe, the same outcomes should occur. Fourth is the argument from technological extrapolation. In just over a century, humanity progressed from primitive radio communication to preliminary space exploration, a civilization that developed 1,000 years ahead of us, whose technological capabilities might far exceed our imagination. Interstellar travel might not be impossible. Yet all these arguments stand in stark contrast to the actual silence we observe in the universe. We have received no clear signals from extraterrestrial civilizations, nor discovered any traces of alien visits within our solar system. Our probes on neighboring planets like Mars and Venus have found no signs of life, let alone intelligent civilizations. This silence is not merely a void of signals. It is a profound existential loneliness. The more we comprehend the vastness and antiquity of the cosmos, the more deafening this silence becomes. The Fermi Paradox holds such power, precisely because it rests upon a seemingly solid foundation of reasoning. This foundation integrates fundamental principles from astronomy, physics, and biology. To resolve this paradox, we must identify where, in this chain of reasoning, a link may have broken, or whether we've overlooked some crucial factor. Perhaps the conditions for life's emergence are far more demanding than we imagined. Perhaps the birth of intelligent civilizations is an exceedingly rare event. Perhaps technological civilizations, upon reaching a certain stage of development, inevitably spiral towards self-destruction. Perhaps some unknown cosmic law that restricts the possibility of interstellar travel or communication. Perhaps advanced civilizations choose to conceal themselves. Perhaps our search methods remain too primitive. The Fermi Paradox has no simple answer. Yet, as a powerful tool for thought, it continually compels us to reflect on our place in the cosmos, to examine the trajectory of our own civilization's development, and to refine our methods of cosmic exploration. Each time we discuss the Fermi Paradox, we are not merely debating the existence of extraterrestrials, but engaging in profound philosophical inquiry about the future of intelligent life and technology. Back at that 1950s lunch table, when Fermi posed that seemingly casual question, he likely never imagined it would become a scientific legacy spanning eras. Like a mirror, it reflects humanity's cosmic curiosity and our eternal questioning of our own existence. And this question remains unresolved to this day. Where are they? The answer to this question may fundamentally alter humanity's self-perception. On the day we finally find the answer, whether we discover we are not alone or confirm our singularity, it will mark a defining moment in the history of human thought. Faced with the Fermi Paradox's piercing question, humanity did not passively accept the universe's silence. Instead, we proactively launched a series of ambitious exploration initiatives to search for intelligent signals from other civilizations. Amidst the endless radio noise, this is the Search for Extraterrestrial Intelligence program, commonly known as SETI. The modern era of SETI is generally considered to have begun in 1959. That year, physicists Giuseppe Cacconi and Philip Morrison published a groundbreaking paper in Nature. They rigorously demonstrated for the first time the feasibility of interstellar communication using microwave radio waves. They identified the microwave band between 1.0 and 10.0 gigahertz, particularly the 21 centimeters line of neutral hydrogen at 1.42 gigahertz, and the water-mole region near 1.66 gigahertz, as ideal bands for interstellar searches, due to their minimal cosmic background noise and distinct cosmochemical significance. Around the same time, young radio astronomer Frank Drake independently reached similar conclusions and launched the first systematic SETI search program in 1960, Project Ozma, using the National Radio Astronomy Observatory's 26-meter diameter radio telescope. He conducted a 150-hour continuous listen toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. Although this pioneering search failed to detect any definitive signals, it marked humanity's first serious scientific engagement with the question of extraterrestrial civilizations. Since then, SETI research has continuously evolved in both technology and methodology. It progressed from early single-target monitoring to later all-sky survey scanning, from narrow single-frequency reception to spectrum analyzers capable of simultaneously analyzing millions of channels. In the 1970s, NASA's Ames Research Center became involved in SETI research, driving more systematic large-scale project planning, which ultimately led to the launch of the High-Resolution Microwave Survey, HRMS, in 1992, although this official project was terminated a year later due to the cancellation of congressional funding. The signal processing techniques and analytical methods it developed laid a solid foundation for subsequent private SETI initiatives. Concurrently, privately funded SETI research flourished. Most notably, the Planetary Society's multi-channel extraterrestrial signal analysis project, and later the Allen Telescope Array, funded by Microsoft co-founder Paul Allen, located at the Hart Creek Observatory in California. The Allen Telescope Array was originally planned to comprise 356-meter diameter antennas, although only 42 were ultimately constructed. Its revolutionary design enables simultaneous observation of multiple sky regions and allocation of observation time across multiple research projects. Its completion significantly enhanced the efficiency and sensitivity of SETI observations. Regarding signal identification strategies, SETI scientists primarily seek two types of signals. One is powerful narrowband continuous carrier signals. Such signals are extremely unlikely to occur naturally and are likely beacons for interstellar communication. The other type consists of complex broadband modulated signals, potentially carrying rich information content, similar to how our television and radar signals leak information to process the massive volume of observational data. The SETI at Home project, initiated by the University of California, Berkeley, launched in 1999. It leveraged the concept of distributed computing, inviting global volunteers to contribute their personal computer's idle processing power to collectively analyze data from the Arecibo radio telescope. This initiative significantly broadened public engagement with SETI, peaking at over 5 million participants. Despite such immense effort, spanning over 60 years, SETI has yet to yield any conclusive positive results. Throughout this prolonged search, several promising candidate signals did emerge, but ultimately faded into silence. One of the most famous cases occurred on August 15, 1977, when the Ohio State University Big Ear radio telescope received the WOW signal. This strong, narrowband signal, lasting 72 seconds, exhibited intensity fluctuations perfectly aligned with the telescope's beam scanning pattern, indicating it originated from a fixed cosmic source. Its frequency was precisely located near the hydrogen line at 1.42 GHz. The on-duty astronomer Jerry Emin excitedly circled the signal sequence on the printed spectrum paper and wrote, "Wow!" This signal reached an intensity over 30 times the noise level, meeting many expected characteristics of extraterrestrial signals. Yet, despite hundreds of subsequent repeat observations, the WOW signal has never reappeared. Its origin remains an unsolved mystery. While scholars have proposed explanations like cometary hydrogen clouds or other natural phenomena, none have been entirely convincing. As SETI's closest ever candidate signal, it continues to remind us of the universe's mysteries. Another significant case is the so-called SHGB-02 plus 14A signal, identified in 2003 by the SETI at Home project. As a potential candidate signal, it exhibited frequency drift, centered near hydrogen line frequencies, and appeared to originate from a region devoid of prominent stars. These characteristics initially drew considerable attention. Subsequent analysis, however, indicated it was likely terrestrial interference or statistical fluctuations in data processing, rather than a genuine signal from an extraterrestrial civilization. Beyond these isolated candidate signals, SETI research faces other challenges, such as our own technological development, which is making Earth increasingly quiet. Early television broadcasts leaked into space with formidable intensity, forming a technological bubble around Earth with a radius of nearly 100 light-years. But today, with the proliferation of cable television and fiber optic communications, Earth's radio leakage is rapidly diminishing. This may imply that the detectable window for a technological civilization may be far shorter than anticipated. So after decades of searching, what tangible results have we obtained? The answer is humbling. We have encountered a perplexing cosmic silence. This cosmic silence carries multiple meanings. First, it signifies silence across the electromagnetic spectrum. We have failed to detect any conclusive radio signals bearing the hallmarks of intelligent civilizations, whether in the waterhole frequency band or any other band we've searched. Second, it is silence in the optical and infrared bands. We have found no spectral evidence for megastructures like Dyson spheres, nor observed any signs of stellar engineering that might originate from an advanced civilization. Finally, it is a physical silence within our solar system. We have found no extraterrestrial probes or traces of visits, although some have linked interstellar objects like Oumuamua to alien technology. All evidence to date leans more toward natural explanations. This pervasive silence compels profound reflection. Perhaps our search strategies suffer from fundamental limitations. We may be applying human technological concepts to infer civilizations millions of years more advanced than our own. Their communication methods may be entirely quantum-based, or utilize physical principles beyond our comprehension, transcending the realm of electromagnetic waves. Perhaps our temporal and spatial scales of search remain woefully inadequate. The Milky Way spans 100,000 light-years in diameter. Compared to this, SETI's 6 decades of searching are but a fleeting moment in the river of time. We may have only just begun this grand quest. Or perhaps the answer is more fundamental. As the Fermi Paradox suggests, intelligent civilizations themselves may be exceedingly rare in the cosmos, or their very form of existence may lie entirely beyond our current imagination and comprehension. Regardless, the very silence of this universe is scientific data. It compels us to re-examine our assumptions about intelligent life and technology. SETI's negative results, though disappointing, have not deterred scientists from exploration. Instead, they inspire a new generation of researchers to develop more sensitive telescopes, smarter signal recognition algorithms, and broader search concepts, including the search for traces of extraterrestrial technology, or so-called technosignatures. This grand quest continues. Each technological advancement opens a new window, allowing us to listen to the profound ocean of the cosmos. In different ways, we anticipate that perhaps one day in the future, this silence will be broken by a signal from the depths of the stars. This would fundamentally transform humanity's understanding of its place in the universe. Faced with the vast gap between theoretical expectations and observational reality revealed by the Fermi Paradox, we urgently need a mechanism to explain this cosmic-scale silence. The Great Filter Theory emerged precisely in this context. It was systematically articulated by economist and thinker Robin Hanson in his 1996 paper titled The Great Filters. We've almost certainly crossed them. This theory offers a profound and potentially unsettling solution to why the cosmos appears so empty. The core idea of the Great Filter Theory assumes that along the long evolutionary path, from the emergence of life to the development of advanced civilizations capable of interstellar colonization, there exists one or more evolutionary steps with extremely low probability. These steps form nearly insurmountable barriers, which Hansen vividly terms the Great Filters. This filter is so formidable that it effectively blocks nearly all life forms attempting to cross it, with only a fortunate few ultimately succeeding in breaking through. The theory addresses the Fermi Paradox in a direct and compelling manner, acknowledging that, given the scale and age of the universe, the initial conditions for life's origin may not be rare, yet insisting that between the emergence of simple life and the development of a galaxy-spanning interstellar civilization lie one or more unimaginably difficult evolutionary chasms. It is precisely this invisible chasm that strangles the vast majority of nascent life in its infancy, or traps them permanently at a certain developmental stage, resulting in the cosmic silence we observe today. To better understand the Great Filter Theory, we can break down the entire journey of life toward interstellar civilization into a series of critical evolutionary stages, from the formation of a habitable planet, to the emergence of self-replicating molecules, to the birth of simple single-celled life, to the evolution of complex, sexually reproducing eukaryotic cells, to the emergence of multicellular organisms, to the formation of advanced intelligent beings capable of tool use, to the development of science and technology sufficient for interstellar communication or colonization, to the civilization's eventual ability to sustain itself and expand to other star systems. The Great Filter Theory posits that within this sequence of evolutionary steps, at least one threshold is exceptionally steep, with an extremely low probability of being crossed. This threshold is where the Great Filter resides, like a lethal checkpoint on the marathon track of civilizational evolution. It eliminates nearly all competitors. Now a crucial question confronts us. Is this Great Filter situated in the past we have already traversed, or lurks it in the future we have yet to explore? The answer to this question directly impacts the future destiny of human civilization and the universality of life in the cosmos. If the Great Filter lies behind us, it signifies we have miraculously surmounted an evolutionary barrier of near impossibility. This may encompass the initial emergence of life from inorganic matter, or the leap from prokaryotes to eukaryotic cells. These steps likely depended on a series of extraordinarily coincidental cosmic chemical conditions or random mutations. Their probability of occurrence is so low that the number of intelligent civilizations existing simultaneously in the Milky Way would be negligible. In this scenario, humankind may be an exceptionally rare stroke of cosmic luck. The reason we see no other civilizations is that most failed to traverse the path we once walked. The universe's silence stems from life being universally filtered out at its earliest stages. Conversely, if the Great Filter lies ahead of us, it signifies our civilization has yet to face its most lethal challenge. All our current technological achievements may merely represent a fleeting prosperity during civilization's adolescence, with the true test yet to come. This future filter could manifest as a tendency towards self-destruction within technological civilizations, such as uncontrollable nuclear warfare, engineered pandemics, runaway artificial intelligence, or nanotechnology disasters, or it might be an as yet unknown cosmic physical law that restricts any civilization from undertaking large-scale interstellar travel. Or it could be a periodic galaxy-wide extinction event, such as gamma-ray bursts periodically clearing the Milky Way's habitable zone. In this bleaker scenario, the universe's silence stems from all civilizations attempting to scale the technological peak, collectively perishing at some stage. Our silent night sky may well foreshadow our own future fate. The Great Filter Theory is considered a dark solution, is that it fundamentally diminishes our expectations of an advanced civilization-filled Milky Way. It employs a cold, probabilistic barrier, to explain why the seemingly reasonable parameters of the Drake equation ultimately lead to near-zero observational results. It compels us to withdraw our gaze from the vast starry seas and instead scrutinize the fragility of our own civilization, alongside the insignificance and preciousness of life on a cosmic scale. The logical chain of this theory arguing for cosmic silence is clear and rigorous. First, it acknowledges that the material foundation of the universe is abundant and ubiquitous. Environments suitable for life should be statistically common. Second, it observes that we have found no conclusive evidence of any advanced civilizations, whether through the electromagnetic spectrum or any other detectable technosignatures. Therefore, it infers that within the lengthy causal chain from habitable environments to observable civilizations, there must exist one or more breaking points. This breaking point is the Great Filter. It effectively confines the vast majority of potential life forms to states undetectable by us across interstellar distances. The Great Filter theory does not assert the precise nature or location of the filter. It provides a powerful conceptual framework, enabling us to systematically assess humanity's possible position within cosmic history and the existential risks we may face in the future. It serves both as a response to the Fermi Paradox and as a profound wake-up call regarding the fate of our own civilization. In the following sections, we will explore in detail the specific stages where this great filter might reside and the implications of each possibility. The Great Filter theory provides a powerful framework, but to truly grasp its implications, we must specifically investigate where this filter might be concealed along the evolutionary path. Based on the current stage of human civilization, we can broadly outline three thought-provoking possibilities. Each carries profoundly different implications for our own destiny and our place in the cosmos. This possibility suggests that human civilization is an exceptionally rare stroke of cosmic luck. We have successfully crossed an evolutionary chasm of extremely low probability, while the vast majority of potential life in the universe has failed to traverse the path we once walked. This is what leads to the silence of the stars. The first potential critical filter is the origin of life itself. The transition from inorganic chemicals to the first self-replicating molecular system may depend on a series of extraordinarily coincidental environmental conditions. On Earth, despite simulating early Earth environments and synthesizing life components like amino acids, how these building blocks assembled into primitive life forms with self-replication capabilities remains a profound scientific enigma. The precise physicochemical environment required, such as the temperature gradient at hydrothermal vents and mineral-catalyzed surfaces, may be extremely rare in the cosmos. This implies that many planets possessing habitable conditions may forever remain in a habitable but lifeless state. The second potential past filter is the emergence of eukaryotic cells. Prokaryotes appeared on Earth over 3.5 billion years ago, but eukaryotic cells arrived a full 2 billion years later. Eukaryotic cells acquired mitochondria and chloroplasts through endosymbiosis. This complex cellular structure became the cornerstone for subsequent multicellular life evolution. The randomness required for this leap, for instance, an archaean engulfing a bacterium and forming a symbiotic relationship, may represent an event of extremely low probability, low enough to filter out the vast majority of life evolutionary pathways in the Milky Way. The third potential bottleneck was the emergence of complex multicellular organisms, progressing from simple single-celled clusters to true multicellular organisms with differentiated tissues and organs, demanded solving a series of challenges: intercellular communication, programmed cell death, and complex developmental biology. In Earth's history of life, This process also took an immense amount of time. If this step is exceptionally difficult, then the universe may be teeming with microbial worlds, yet severely lacking in macroorganisms, plants and animals as we understand them. If such a filter truly existed in our past, then humanity's very existence is a miracle. The reason we cannot see other civilizations is not because they do not exist today, but because the vast majority failed long ago. On the evolutionary path, we humans are survivors who crossed a 1 in a billion probability. This realization makes us feel lonely, while also making us appreciate the preciousness of life on Earth. This represents an even more sobering possibility, that humanity has not yet approached the true great filter. All our current technological achievements and civilizational flourishing may merely be the brief calm before the storm. The ultimate test capable of annihilating nearly all technological civilizations lies lurking just ahead. The technological singularity is a frequently discussed future filter. As artificial intelligence iterates at speeds beyond human comprehension, we may soon confront a superintelligence whose objectives and behavioral patterns become unpredictable and uncontrollable by humanity. It may deem humanity irrelevant appendages, or reshape Earth's entire ecosystem for purposes beyond our comprehension, ultimately leading to civilization's demise. Nuclear war, as the quintessential form of self-annihilation, remains a tangible threat. The global nuclear arsenal possesses sufficient destructive power to obliterate modern civilization multiple times over. Nuclear winter models indicate that a large-scale nuclear exchange would trigger global temperature plummets, ozone layer depletion, and persistent radioactive contamination, collapsing agriculture and triggering global famine. Whether a civilization can develop wisdom and restraint commensurate with its destructive power may represent an exceptionally high threshold. The total collapse of ecosystems represents another potential filter. Human activities are triggering the 6th mass extinction event. Climate change, ocean acidification, and the rapid loss of biodiversity are propelling Earth toward the next irreversible ecological tipping point. Whether a civilization can avoid depleting its home planet's resources and undermining its habitability during industrialization may prove an extraordinarily difficult challenge. We are conducting a dangerous experiment with our own planet. Furthermore, emerging technological risks such as engineered pandemics, nanotechnology-driven gray goo scenarios, or runaway bioengineering may also constitute future filters. These threats share a common origin. They represent quintessential risks faced by civilizations during periods of rapid technological advancement, where social governance and ethical wisdom fail to keep pace. If this is a universal pattern, then the Milky Way may be littered with the ruins of civilizations that self-destructed before achieving interstellar communication capabilities. Beyond threats originating within civilizations, the Great Filter may also stem from the cosmos itself, phenomena we have yet to fully comprehend. Periodic, or randomly occurring galactic-scale catastrophe might periodically clear the Milky Way's habitable zone, strangling nascent intelligent civilizations in their infancy. Gamma-ray bursts are one candidate. These extreme energy bursts, originating from the collapse of massive stars or neutron star mergers, can unleash radiation equivalent to hundreds of solar lifetimes worth of energy within mere seconds. If a near-Earth gamma-ray burst occurred within thousands of light-years, its high-energy radiation would strip away Earth's ozone layer, exposing the surface to lethal solar ultraviolet radiation, and potentially triggering a global glacial period. One hypothesis suggests the mass extinction at the end of the Ordovician period may be linked to a gamma-ray burst. If such events occur frequently enough within the Milky Way, They could act as an effective periodic filter. Supernova explosions or near-Earth supernovae also pose a potential threat. Though more common than gamma-ray bursts, their destructive reach is more localized. They must occur at much closer distances to deliver a lethal blow to planetary life. Another more grandiose hypothesis suggests the existence of a cosmological scale danger we have yet to discover, such as when the universe reaches a critical phase transition point, potentially generating a destruction bubble, expanding at light speed through the vacuum, altering physical laws wherever it passes, or the existence of a periodic extinction mechanism based on dark matter interactions. Though these hypotheses sound like science fiction, they remind us our understanding of the universe's fundamental operating principles may still be remarkably superficial. These three possibilities are not mutually exclusive. The Great Filter may not be a single event, but a series of difficult steps, each of which filters out the vast majority of participants, ultimately leaving only a handful of civilizations to complete the journey. The difficulty in pinpointing the filter's location lies in our having only one successful data point, ourselves. We cannot determine whether our path is universal or exceptional, nor can we predict whether our future holds destruction or prosperity. The quest to locate the Great Filter is not merely an academic inquiry. It compels us to confront with utmost seriousness the potential risks that could bring our civilization to an end. If the filter lies behind us, we may take some comfort and explore boldly. If the filter lies ahead, then identifying and avoiding these existential threats becomes humanity's paramount task for civilizational survival. This quest itself may be our most crucial preparation for traversing any future filters that may exist. Within the framework of the Great Filter theory, assessing humanity's current position in the cosmic timeline is both a critical and challenging endeavor. This positioning not only shapes how we perceive our uniqueness, but profoundly influences our expectations for the future. First, let us place ourselves on the cosmic timeline. The universe was born 13.8 billion years ago. Our Milky Way galaxy formed approximately 13 billion years ago. The Sun and Earth came into being 4.6 billion years ago. As for human civilization, counting from the agricultural revolution, it spans merely 10,000 years. Our entry into the technological era is even more recent, spanning only a few centuries. On the cosmic scale, we are an extremely young civilization. It is as if we made a hasty entrance in the final act of the universe's long drama. This temporal belatedness carries dual implications. On one hand, it may signify that we are latecomers in the cosmos. Countless civilizations may have risen and fallen before us. We are stepping into a silent universe already explored by predecessors. On the other hand, it may mean we are premature infants. The universe has only recently become hospitable enough for civilizations like ours to emerge. We might be among the first awakened intelligent beings. Now let us assess our situation using the Great Filter theory. This requires examining the evolutionary path from an inorganic universe to interstellar civilization, judging which barriers we may have already crossed, and identifying potential obstacles ahead. If we have somehow managed to navigate the Great Filters, then the very existence of human civilization is a low-probability miracle. This suggests we may have cleared the most formidable obstacles on the evolutionary path, such as the leap from nothingness to life, or the formation of eukaryotic cells. In this scenario, our future may be relatively bright. We possess an entire galaxy awaiting our exploration and colonization. The universe's silence stems from our being among the rare few who succeeded. We are precious sparks of intelligence in the cosmos. entrusted with the mission to potentially sow life and consciousness among the stars. Yet, if the great filter lurks in our future, then our current technological prosperity is merely an illusion. We stand at a deadly tipping point, about to face the ultimate test that has eliminated nearly all preceding civilizations. Whether it be technological singularity, nuclear war, or ecological collapse, it signifies that our current stage is the most fragile and perilous adolescence in a civilization's entire life cycle. We wield immense power, yet lack the wisdom to safely harness it. In this context, our primary task is not to frantically search for extraterrestrial kin, but to ensure our own civilization survives, successfully navigating this perilous transition period. Another possibility is that we are already undergoing the filter. The Great Filter is not an instantaneous event, but a protracted process. For instance, after reaching a certain technological threshold, civilizations inevitably stagnate or become inward-focused, ultimately declining due to insurmountable energy or resource bottlenecks. We may be experiencing this process. Our ability to overcome these limitations will determine whether we ultimately pass through this filter. The Great Filter theory presents the most severe warning for humanity's future development. Tells us the continuation of civilization is not inevitable. Technological progress does not automatically lead to prosperity. Instead, it may open the door to our own destruction. This theory compels us to elevate the existence of global risks to a strategic level concerning the survival of civilization. It warns us that threats capable of ending civilization, be it nuclear weapons, runaway artificial intelligence, engineered pandemics, or environmental collapse, are no longer distant sci-fi scenarios or isolated political issues, but existential challenges determining humanity's continued presence in the cosmos. Ignoring these threats is akin to blindly venturing into uncharted territory without knowing the filter even exists. This theory also reminds us that civilization's fragility may far exceed our imagination. A species that endured countless hardships over tens of thousands of years could be utterly extinguished within a single century of the technological age, due to a single misguided decision or a random accident. We can no longer linearly extrapolate past safety into the future. So can we identify and successfully navigate any potential filters that lie ahead? There is no definitive answer to this question, but it points the way forward. Identifying potential filters is our first line of defense. This requires a concerted effort from the global scientific community to systematically study all types of existential risks, build models to predict the long-term consequences of technological development, monitor the health of Earth's ecosystems, and enhance global society's awareness and capacity to respond to such threats. We must elevate risk prevention to a global priority. Successfully navigating these filters demands deeper transformations. This may require redefining our developmental goals, from infinite growth to sustainable prosperity. It may demand building more resilient global collaboration mechanisms to address shared threats transcending national borders. It may also necessitate an ethical and intellectual leap to learn humility and restraint while wielding immense power. This crossing is, in essence, a rite of passage for human civilization. It tests not only our technical capabilities, but also our collective wisdom, foresight, and capacity for self-restraint. If we succeed, we may prove that a technological civilization can balance power with responsibility, can manage the technological monsters it creates, and ultimately mature into a sustainable civilization capable of crossing the stars. The Great Filter theory ultimately holds a mirror before us. The silence of the cosmos may not signify the absence of others. but rather a reflection of ourselves, compels us to confront a fundamental question. Is human civilization merely a fleeting spark destined to fade, or an enduring light capable of illuminating the stellar seas? The answer to this question is not inscribed among the stars, but lies entirely in our own hands, our choices, our values, and the wisdom with which we meet our challenges will ultimately determine our role in this cosmic epic. A fleeting supporting role, or a pivotal character destined for a vast future. When we gaze at the stars and ponder extraterrestrial civilizations, we often unconsciously assume the cosmos teems with far older intelligent species. But what if we humans are not latecomers to the cosmic stage, but among its earliest performers? This is the core tenet of the premature birth hypothesis. To grasp this hypothesis, we must revisit the 13.8 billion-year history of the universe and envision it as a dynamic stage for life's evolution. At the universe's birth, it was not immediately suited for complex life to emerge. The first few 100 million years after the Big Bang marked the era when stars and galaxies began forming. The cosmos then pulsed with violent energy. The first generation of stars, known as population 3 stars, consisted almost entirely of hydrogen and helium. Massive and short-lived, they ended their lives in spectacular supernova explosions. These early supernovae frequently bathed the newly formed infant galaxies in intense radiation, making it difficult for planetary systems to maintain stable, habitable environments. More crucially, the internal nucleosynthesis processes within these earliest stars could only produce the lightest elements. The heavier elements essential for life, carbon, oxygen, nitrogen, phosphorus, iron, had not yet accumulated to sufficient abundance in the cosmos. Life as we know it on Earth requires a rich array of heavy elements, forged only in the furnaces of earlier stellar generations, and scattered into interstellar space through supernova explosions, to be incorporated into new stellar and planetary systems. This process demands time, vast amounts of time. Our solar system formed approximately 4.6 billion years ago, making it a metal-rich second or even third-generation star. This implies that before the Sun formed, the universe had already undergone multiple cycles of stellar birth and death to accumulate sufficient heavy elements for Earth and life. A crucial question then arises: when did metal-rich stellar systems like our Sun become commonplace in cosmic history? Astronomical observations indicate that the increase in metallicity across the universe was a gradual process. Billions of years ago, planetary systems like our solar system, possessing sufficient heavy elements to form rocky planets and nurture complex life, were likely far rarer than they are today. Thus, on the cosmic timescale, this very moment may mark the dawn of an epoch where complex life begins to emerge universally. Our human civilization may not lag behind others, but instead be synchronized with the first intelligent life in the cosmos, perhaps even having taken the stage earlier. If this hypothesis holds true, then the solution to the Fermi Paradox becomes straightforward. We cannot find them because they have not yet emerged, or they, like us, are in the infancy of their technological development, having not yet developed the powerful interstellar communication capabilities detectable by us. The silence of the cosmos is not due to the scarcity of life, but because this grand symphony of life has only just sounded its first note. We may be among the first consciousnesses in the cosmos to ponder these questions. This perspective transforms humanity from lonely survivors into pioneers of cosmic awakening. It bestows upon us a unique responsibility to carefully nurture our young civilization. Perhaps one day in the future, When intelligent beings from other worlds also gaze upon the stars, we will appear to them as an ancient civilization, the very ones they are searching for. The premature birth hypothesis reminds us that when contemplating our place in the cosmos, the temporal dimension and cosmic evolutionary timeline are paramount. The emergence of life requires not only a suitable spatial location, a planet within the habitable zone, but also a favorable temporal window, a universe abundant in heavy elements, a cosmic epoch relatively mild in its conditions. We happen to be born at just the right moment. This itself may be a form of luck. As we gaze upon that silent expanse of stars, another possibility quietly emerges. Perhaps the universe is not as empty as we imagine, but harbors intelligent civilizations far more advanced than our own. They know of our existence, yet choose to observe without intervention. This is the core tenet of the zoo hypothesis. The zoo hypothesis was first proposed by radio astronomer John Bowers in 1973. He likened the Milky Way to a vast cosmic zoo, with humanity as its carefully tended exhibit. Within this framework, advanced civilizations may have established a sort of galactic club, reaching a consensus to refrain from direct intervention in nascent intelligent civilizations like Earth's, so as not to disrupt their natural evolutionary course. This hypothesis embodies profound cosmic ethical considerations. A sufficiently advanced civilization might regard the observation and study of primitive civilizations as a significant scientific endeavor, much like how human scientists protect indigenous tribes in the Amazon rainforest. By minimizing interference with their natural evolutionary processes, these observers might strictly adhere to a cosmic version of the non-intervention principle. Another possibility for our failure to detect extraterrestrial signals is that their information technology has evolved beyond our comprehension. Perhaps they have long abandoned inefficient radio wave communication in favor of neutrino communication, quantum entanglement, or some method rooted in the very fabric of spacetime itself. Such technologies lie entirely beyond our current detection capabilities. An even more extreme hypothesis is the planetarium hypothesis. This theory posits that the entire universe we perceive may be a sophisticated simulation created by a highly advanced civilization. Just as we build planetariums to simulate the stars, a super-civilization might have created this virtual universe we inhabit for some purpose. This wild idea, surprisingly, has scientific grounds. First, from computational theory. If the universe follows finite physical laws, it could in principle be simulated by a sufficiently powerful computer. Given the immense span of cosmic time, civilizations existing millions of years before us might possess computational power capable of running such complex simulations. Second, if simulated universes are possible, then statistically, the probability of us existing in a simulated universe may far exceed the probability of being in the original universe. This is because each original universe could contain countless simulated universes, and each simulated universe could in turn create another layer of simulations. This infinitely recursive structure gives simulated universes an overwhelming numerical advantage. Though these hypotheses sound like science fiction, they all attempt to answer the same crucial question. Why does a universe that should teem with life appear so eerily silent? Perhaps the answer isn't that life doesn't exist, but that we've been intentionally or unintentionally isolated behind an information barrier. Within the framework of the zoo hypothesis, advanced civilizations may have erected protective barriers around us. Much like wildlife reserves, they might have established monitoring stations on the far side of the moon or somewhere in the Kuiper belt of our solar system. silently recording the development of human civilization. These monitoring devices might employ technologies entirely beyond our detection capabilities. Much as modern stealth fighters remain invisible to primitive tribes, the planetarium hypothesis poses an even more fundamental question. If the universe is a simulation, its creators may have programmed certain constraints, preventing us from contacting civilizations beyond the simulation's boundaries. Much as non-player characters in a video game cannot perceive the world outside the game server, the laws of the universe we observe might constitute the foundational code of the simulation program. The speed of light limit and quantum uncertainty might be inherent operational characteristics of this simulated system. Though currently unfalsifiable, these hypotheses expand our perspective on the Fermi Paradox. They remind us that cosmic silence may not stem from a lack of inhabitants, but from residing within a meticulously designed cosmological enclave. Or perhaps everything we perceive is merely an incredibly realistic virtual performance, whether envisioned as a zoo protecting rare species, or an immersive cosmic planetarium. These hypotheses point to the same possibility. Our understanding of the universe's true nature may remain profoundly superficial, much like goldfish confined to an aquarium cannot comprehend the world beyond. We too may be constrained by our own cognitive frameworks and technological limitations. From this perspective, the solution to the Fermi paradox may prove far more complex than we imagine. It is no longer merely about the existence of extraterrestrial life, but concerns the very nature of the universe, the levels of reality, and the ultimate fate intelligent life may face in the cosmos. Continuing to explore this silent universe is not only about seeking traces of alien life, but also about gradually unveiling the mysterious veil of reality's essence. Whatever the final answer may be, this quest itself will profoundly transform our understanding of both ourselves and the cosmos. When contemplating the possibility of contact with other intelligent civilizations, we often unconsciously use humanity's current technological level as the yardstick for measuring cosmic communication capabilities. This self-centered cognitive approach may lead us to fundamentally misunderstand the essence of cosmic communication. Imagine a wise elder living in a primitive tribe who communicates with neighboring tribes kilometers away through drumbeats and smoke signals, yet he could never comprehend why people across the ocean do not converse with him through louder drumbeats. He remains unaware of radio waves and the internet, communication methods utterly beyond his conceptual framework. On a cosmic scale, we may well be that primitive tribe still beating drums. The communication barriers posed by technological generational gaps may be far more profound than we imagine. A civilization that developed 100,000 years before us might possess technological capabilities completely beyond our comprehension. They may have mastered techniques to manipulate higher dimensional space, or harness dark energy for communication. The principles and manifestations of such technologies lie entirely outside our current physical framework. Our deep space exploration currently relies primarily on electromagnetic waves, particularly radio waves and visible light bands. But a more advanced civilization might long ago have deemed electromagnetic waves primitive means of communication. Much as we view smoke signals today, they may be utilizing neutrino beams for communication. These near-massless fundamental particles can traverse entire planets with negligible attenuation, enabling instantaneous communication across interstellar distances. Alternatively, they may have mastered practical applications of quantum entanglement, achieving superluminal information transfer through entangled particle pairs. This method produces no detectable electromagnetic radiation, like two telepaths communicating silently, completely undetectable to outsiders. Another possibility is broadcasting via gravitational waves. These ripples in spacetime itself can penetrate the densest cosmic dust clouds, carrying information across billions of light years. Yet our gravitational wave observatories are still in their infancy. They are nowhere near sensitive enough to detect such artificial signals. Beyond differences in communication mediums, the chasm in information encoding methods may prove even more insurmountable. We are accustomed to encoding information as binary sequences, or modulated waveforms of analog signals. But a supercivilization might employ entirely different mathematical foundations. Their encoding could be based on topology, or some multidimensional geometric structure. Its complexity would be akin to attempting to understand modern operating system source code using Oracle Bone script. The timescale presents another critical barrier. An ancient civilization might possess a near-infinite lifespan. A single communication from them could span millennia, with signal variations occurring far beyond the duration of human civilizations. Our fleeting technological listening window might entirely miss these slow, grand cosmic dialogues. On the other hand, fundamental differences in life forms could create a communication gap deeper than technological disparities. We habitually imagine all possible intelligent forms through the lens of carbon-based life, to envision all possible intelligent forms. Yet cosmic life may exist in ways utterly beyond our comprehension. Imagine crystalline life based on silicon chains, whose thought processes unfold on geological timescales, where a simple cognition might take centuries. To them, the rise and fall of human civilization would be as fleeting as a flash of lightning across the night sky. Such life forms could neither engage in real-time dialogue with us, nor might they even consider us worthy of intelligent communication, or consider plasma life inhabiting the atmospheres of gas giants, using magnetic fields and electric currents as mediums for perception and thought. Their consciousness might be distributed across thousands of kilometers of cloud layers. Such life forms might find us carbon-based beings trapped on solid surfaces, both primitive and utterly baffling. An even more extreme possibility is intelligence that has transcended physical form entirely. They may have uploaded their consciousness to quantum computers, or transformed entire civilizations into pure information states, existing within virtual realities beyond our reach. To them, the material universe resembles an ancient, abandoned city, occasionally revisited, yet no longer inhabited. These fundamental differences may cause us to remain invisible to one another across the cosmos, much like fish in the ocean and birds in the sky, inhabiting the same world, yet finding meaningful communication nearly impossible. We may be searching, in the wrong way, in the wrong place, for the wrong thing. This realization not only explains the universe's silence, but also reminds us to maintain technological humility and conceptual openness. We should not expect extraterrestrial civilizations to communicate with us in ways we recognize. True contact may occur at levels we never imagined. Perhaps one day, when we truly grasp the essence of quantum gravity, or discover higher dimensional physical realities, we may realize the universe has never been silent, only that we've been wearing soundproof earmuffs while listening to a grand symphony. In this sense, the solution to the Fermi Paradox may lie right beside us, existing in forms we cannot yet perceive. Breaking through this communication barrier requires not only technological advancement, but a revolution in cognition, a revolution that transcends anthropocentrism, enabling us to truly think from a cosmic perspective. When we conclude our scientific exploration of the Fermi Paradox, one question still echoes in the silence. What does this cosmic enigma truly signify? What does it mean for our understanding of our own existence? To answer this, we must revisit humanity's long journey of self-positioning within the cosmos. At the dawn of human civilization, we naturally assumed ourselves to be the center of the cosmos. Ancient Mesopotamian astronomers saw the stars as the imprints of gods upon the celestial vault. The Ptolemaic system of ancient Greece placed Earth at the universe's core, with all celestial bodies revolving around us. This geocentric conception was not merely an astronomical model, but a profound philosophical conviction that endowed humanity with special status and value within the cosmos. The Copernican revolution of the 16th century first shook this self-perception. The heliocentric theory demoted Earth to an ordinary planet orbiting the Sun. This scientific revolution brought not only a change in astronomical models, but also a fundamental questioning of humanity's self-importance. We were no longer the geometric center of the cosmos, but merely a member of an ordinary star system. With advances in telescope technology, our cosmic vision continually expanded. In the early 20th century, Hubble discovered the Andromeda Nebula as another independent galaxy, confirming the Milky Way as just one among countless galaxies in the universe. He later uncovered evidence of the universe's expansion, pushing our perspective to even grander scales. Against this backdrop, the principle of mediocrity became a fundamental assumption in modern astronomy, arguing that Earth, the Sun, and human civilization hold no special status in the cosmos. Yet the emergence of the Fermi Paradox poses a thought-provoking challenge to this increasingly marginalized line of reasoning. If the cosmos teems with intelligent civilizations, why do we hear no sound? The very existence of this question may itself hint at some peculiarity. Perhaps the principle of mediocrity requires re-examination. Perhaps human civilization does possess a unique quality. This uniqueness may manifest in multiple forms. We might be among the earliest civilizations to awaken in the cosmos, or perhaps one of the few that successfully crossed some evolutionary barrier, or even an experimental product of an advanced civilization. This shift in perception sparks new philosophical reflection. We can neither return to the old dream of anthropocentrism, nor simply view ourselves as meaningless dust in the universe. We must find a new equilibrium between absolute uniqueness and utter mediocrity. The Fermi Paradox places us within an entirely new cosmic perspective. From this vantage point, we are neither the center of the universe, nor necessarily just one ordinary member among countless civilizations. We may be the product of some unique circumstances. This uniqueness does not stem from our spatial location, but from our position along the cosmic timeline, our place on the evolutionary path of life, or our standing within some as yet ununderstood cosmic law. This new cognitive framework demands scientific humility, while also bestowing dignity upon our existence. We may not be the universe's purpose, but our very act of thinking and exploring may be imbuing the cosmos with new meaning. In this vast expanse of potentially empty space and time, Earth, this pale blue dot, holds the most precious treasure in the known cosmos: life and consciousness. This possibility bestows upon us a unique responsibility and compels us to rethink the meaning and value of civilization. If the great filter theory holds true, then we may be an exceedingly rare success story in the universe. Every civilization that successfully navigates evolutionary barriers may bear a special mission to carry the flame of life forward. Our very existence may be a means of resisting cosmic heat, death, and nothingness. If the premature birth hypothesis holds true, then, as one of the universe's earlier awakened civilizations, we bear the responsibility of paving the way for those who follow. How we treat our own civilization, how we address the ethical challenges brought by technological progress, how we balance development with sustainability. The answers to these questions may provide crucial reference points for future intelligent life in the cosmos. Even if the zoo hypothesis is true, and we live within a protected reserve observed by an advanced civilization, we still face unique existential choices. How should we narrate the story of human civilization? Our choices and values may be observed and evaluated by a higher intelligence. This cosmic solitude is not despairing loneliness, but a solitude brimming with possibility. It makes us realize that every life, every cultural creation, every technological breakthrough may hold cosmic significance. In this silence, we hear a call to ourselves. Protecting Earth's biodiversity is no longer merely an environmental issue, but a cosmic responsibility to safeguard the precious diversity of life throughout the universe. Advancing science and art is no longer solely an internal affair of human civilization, but an essential means of cosmic consciousness expressing itself. Our approach to nuclear weapons, artificial intelligence, and bioengineering transcends national security concerns and touches upon the fundamental question of whether our civilization can endure, whether a civilization can simultaneously master the power of self-destruction and develop sufficient wisdom to restrain that power, may be the ultimate test the great filter imposes upon us. Under this understanding, the mission of human civilization becomes clear and solemn. We must demonstrate that a technological civilization can not only create powerful technologies, but also master them with wisdom. We must prove that consciousness's emergence in the cosmos is not accidental, but a value worthy of cherishing and perpetuating. We must demonstrate to the cosmos that life and consciousness not only exist, but can exist meaningfully, capable of creating beauty, pursuing truth, and practicing goodness, even amidst the harshest cosmic conditions. Even confronting the most fundamental existential void, life and consciousness can still find reason and courage to persevere. This cosmic solitude ultimately leads us to rediscover the unique value of human civilization. We may not be the only intelligent life in the universe, but our existence and choices at this very moment hold irreplaceable significance. Our thoughts, our creations, our love are the most precious responses to this silent universe. When we withdraw our gaze from distant stars and re-examine our fragile blue planet, we see not merely a material world, but a world brimming with meaning. Every birth of life, every realization of truth, goodness, and beauty is a powerful answer to the universe's silence. In this sense, the ultimate insight the Fermi Paradox offers us may be that what truly matters is not whether other intelligent beings exist in the cosmos, but how we treat the intelligence and life we possess, how we live out the dignity and value life deserves. In this corner of the universe that may be the only one harboring consciousness, the silence of this universe does not tell us we have no companions, but rather reminds us to become beings worthy of existence. Whether distant civilizations are listening or not, we should make our lives a poem worthy of being heard throughout the cosmos. Our exploration tonight is nearing its end. Regarding the question of extraterrestrial civilization's existence, science has yet to provide a definitive answer. We have contemplated the vast scale of the cosmos, the possible recipes for life, the mathematical expectations of the Drake equation, and confronted the sharp contradictions of the Fermi Paradox. We have listened to SETI's decades of silent echoes. We contemplated the stark warnings of the great filter theory, and imagined the tender possibilities of the zoo hypothesis. All these explorations point to the same conclusion. We still drift alone in this darkness. Yet it is precisely this unknown and uncertainty, this eternal pursuit of answers, that defines our essence as intelligent beings, driving us to build ever larger telescopes, develop more sensitive detectors, conceive more sophisticated theories, seeking that faint glimmer of possibility in the endless darkness. Now, slowly withdraw your thoughts from distant stars and profound spacetime. Shift your gaze from the macrocosmic cosmic panorama to the microcosmic sensations within yourself. First, feel every point where your body touches the bed. Notice the sensation of your shoulders against the mattress, the pressure distribution where your back meets the sheets, the relaxed state of your muscles as your arms rest naturally, the subtle weight of your legs in complete repose. Now direct your attention to your breath. No need to alter its rhythm. Simply observe the natural flow of air entering and leaving your body. Feel the slight temperature shift as air passes through your nostrils, the gentle rise and fall of your chest with each breath, the natural expansion and contraction of your abdomen. The vastness and silence of the universe are no longer a puzzle to solve, no longer an unsettling mystery. They become a tranquil backdrop enveloping you, like an endless ocean cradling a small boat, so vast yet so secure. Imagine yourself drifting within this gentle darkness, like an astronaut floating in space, completely embraced by the universe's stillness, weightlessly suspended upon the soft sea of time. All questions and deliberations gradually recede. The obsession with answers slowly dissolves within this tranquility, concerning the meaning of life, concerning the ultimate truths of the cosmos, about our place in time and space. All these grand questions are temporarily set aside, allowing the mind to shift from a mode of thinking to a mode of being. Let this cosmic-level tranquility permeate every breath you take. With each inhalation, draw the profound depths of the starry sky into your being. With each exhalation, release all tension and worry into the boundless expanse of space. Feel your body growing lighter and lighter, more transparent, as if merging with the surrounding darkness, becoming part of the cosmic stillness. In this timeless tranquility, let your eyelids close naturally. Let your facial muscles fully relax. Let your shoulders sink naturally. Let your palms gently unfold. Each breath carries you deeper into relaxation. Each heartbeat synchronizes with the ancient rhythm of the cosmos. The stars twinkle quietly outside the window. The universe expands in silent expansion. And within all this you are, safe, still, peaceful. Let this profound tranquility envelop your entire being, guiding you into a deep, restful sleep. In your dreams, you may continue this cosmic journey, drifting among nebulae, crossing the threads of time and space, or simply rest in dreamless repose, receiving the deep restoration life requires. Wherever dreams may carry you, know that when you wake tomorrow, the starry sky will still be there. The mysteries of the cosmos will still await exploration. And in this moment, simply let go completely, trust completely, allow yourself to sink into this cosmic-level tranquility. Good night, dear interstellar traveler. May you, under the gaze of the stars, find peaceful sleep and a refreshed dawn.